We all have this picture in our minds of the Milky Way, a beautiful, flat, spiral disk. But it turns out that's not quite the whole story.
Not at all.
In fact, it's a bit, well, twisted. And surprisingly, maybe half of all the spiral galaxies we see out there have this warp in their outer edges.
That's right. And guess what? Our own Milky Way is one of them.
Really? So what are we talking about exactly? A galactic warp?
Yeah, imagine the outer parts of the Milky Way's flat disk bending slightly.
Yeah.
Think like the grim of a hat that's been gently pushed upwards on one side and downwards on the other.
Oh, okay. Like a vinyl record, maybe? Left out in the sun, it gets that slight smooth bend.
Exactly that kind of idea. It's a subtle feature, but it's definitely there in our galaxy's shape.
So for this deep dive, our mission is to unravel the mystery of this warp in our own Milky Way.
Right. What do scientists actually know for sure?
Yeah, and what are the leading ideas? How did it get there? And, what parts are still a complete puzzle?
We'll be digging into the research, primarily drawing on a key review paper to try and get to the bottom of this cosmic quirk.
Okay, so where do we start? This warp isn't exactly brand new, is it? Scientists have known something wasn't quite flat for a while.
That's correct. It's been known for some time. Early studies really focused on mapping out the shape. They used bright young stars, things called Cepheids and obese stars.
And why those particular stars?
Well, the thinking was that these young stars haven't drifted far from the gas clouds where they formed.
Ah, so they trace the gas.
Exactly. They trace the gaseous disk, and that's where the warp is most noticeable. So this early work gave us that first crucial insight. The outer galaxy wasn't just flat. It had this distinct tilted structure.
Makes sense. Follow the young stars to see where the cosmic nurseries themselves are bent. And some of that early work even suggested it wasn't just sitting there bent, but actually moving.
Precisely. Yeah, back in 1993, Miyamoto and his team looked at something called proper motions.
Proper motions. That's how stars appear to move across our sky, right? Over time.
That's it. They looked at thousands of young stars, relatively nearby, and detected the sort of warping motion. Their conclusion was that these stars seemed to lie on a tilted sheet.
Okay.
And this sheet wasn't just rotating around the center of the galaxy like everything else.
Which you'd expect.
Right, but it was also rotating around what they called the nodal line of the warp itself.
The nodal line, that's where the warped part kind of hinges with the flat inner disk.
Exactly. And they even estimated the speed of this extra rotation, the rotation of the warp.
Wow, okay. A tilted rotating section that's also rotating in another way. That's complex. So they got the main rotation speed, around 225 kilometers per second.
Uh-huh.
But this slower rotation of the warp was about 4 kilometers per second per kiloparsec. Just remind us, a kiloparsec is?
It's a big distance unit we use in galaxies, about 3,260 light years. So 4 kilometers faster for every kiloparsec further out along that nodal line.
Got it. But even with these early clues about the shape and this weird motion, the why was still missing.
That's the fascinating part. Even then, the fundamental dynamics, the forces involved, and what actually caused the warp, that remained a big unknown. As Binney pointed out in a review back in '92, and Poggio and others confirmed much later in 2017, the how and why of these warps were still largely mysteries. The shape was getting clearer, but the reasons, still elusive.
So we were starting to get the what, but the why was a big question mark. Then came the Hipparcos satellite. That gave us a much better look, didn't it?
Absolutely. Hipparcos was a huge step up. It provided significantly more precise measurements of those proper motions we talked about. Much better than before.
So you could see further, more accurately.
Exactly. It allowed scientists to investigate the warp in much greater detail, especially for stars further away from us.
And what did Hipparcos find? Did it solve the mystery?
Well, not entirely. In '98, Smart and his collaborators looked at distant OB stars, but towards the galactic anticenter, the direction opposite the galaxy's core from us. They confirmed the overall shape, that bent hat brim idea. Pretty flat out to us. Then turning up towards Cygnus, down towards Vela.
So the basic shape held up. But you said not entirely. Was there a catch?
There was a surprising twist, yes. While the shape seemed okay, the velocities how those distant stars were actually moving were the complete opposite of what you'd expect.
Opposite. Opposite to what?
Opposite to what you'd expect for a warp that's been around a long time and is behaving, stably, whether it's rotating smoothly or precessing that slow wobble.
Wow. So the stars weren't moving like a stable, long-lived warp would predict. That must have really thrown a curveball.
It certainly did. And Dremel and colleagues confirmed this weird velocity pattern later with an even bigger sample of Hipparcos stars, covering the whole galactic plane.
So what did they think was going on then?
They basically proposed two main possibilities. One, maybe the warp is actually short-lived. Perhaps it was triggered relatively recently by, say, an interaction with another galaxy.
Like a gravitational nudge.
Exactly.
Yeah.
They even suggested the Sagittarius dwarf galaxy, which we know has smashed through our disk before, might be the culprit.
Okay, that's one idea. What was the other?
The other idea was, well, maybe there are other big unknown motions happening in the disk. Things like large-scale vertical oscillations, like the whole disk is kind of bouncing up and down in places. And those extra motions could be confusing the signal, making it hard to interpret the velocities purely in terms of a simple warp.
A short-lived warp from a galactic fender bender or some fundamental wobble in the disk we hadn't accounted for. Neither sounds simple. This brings up the question, what were the theories for how a galaxy gets warped anyway? What could cause it?
Well, one really prominent idea involves the dark matter halo.
Ah, the big invisible elephant in the galactic room.
Pretty much. That vast structure of mysterious dark matter surrounding our galaxy. The theory goes, if the flat plane of our visible disk, the stars and gas we see, is tilted relative to the symmetry axis of the dark matter halo.
Like the record is slightly wonky inside its invisible container?
That's a good analogy. Then the gas in the outer parts of the disk might naturally want to settle into the halo's slightly different plane over time.
Okay.
And that settling process could create the tilted disk we see as a warp. And crucially, this tilted disk sitting inside the massive gravity of the halo would then likely precess.
Precess, like a spinning top wobbles.
Exactly like that. A slow wobble as it spins within the halo's influence.
So the dark matter halo, even though we can't see it, could be the puppeteer pulling the strings on the outer disk. That's neat. Did that fit the weird Hipparcos results, though?
Not perfectly smoothly. Idata and his team looked into this halo idea back in 2000. He found something interesting. If the halo is oblate sort of flattened, like a pancake, then any kinematic warp, any warp driven by motion, would actually tend to wind itself up and disappear pretty quickly.
Oh, not good for explaining a persistent warp, then.
But they also found that if the halo is prolate more elongated, like a cigar shape, then warps could persist much longer. It's about how the precession rates work out across the disk in different halo shapes.
So the halo shape matters. Do we know what shape ours is?
That's the tricky part. Our best cosmological simulations, the computer models of how galaxies form, suggest that there should be roughly equal numbers of prolate and oblate halos out there.
So it could be either, which means the halo theory alone might not be the full story.
It seems likely it's a piece of the puzzle, but maybe not the only piece based on that.
Now, you mentioned earlier some other complications, things discovered out near the edge of the disk. Let's open that parenthesis, these rings and streams.
Indeed. Yeah, roughly twice as far out as we are from the center. Astronomers found these big structures, things like the Monoceros ring and these stellar streams like the Triangulum Andromeda streams.
What are they? Just more stars?
They're regions with a higher density of stars, forming these long, extended structures that seem to wrap around the outer galaxy.
And these aren't the warp itself, but they make understanding the warp harder, like trying to see ripples on a pond when there's also leaves floating around making their own waves.
That's a perfect analogy, yes.
Yeah.
The leading idea for these rings and streams is that they're probably the shredded remains of smaller galaxies.
Galactic cannibalism leftovers.
Pretty much. Something maybe like the Sagittarius dwarf galaxy again that got too close and was torn apart by the Milky Way's gravity.
Okay.
And the simulations suggest that these kinds of collisions wouldn't just leave streams of stars. They could also kick off those vertical oscillations in our own disk, the up and down wobbles we mentioned earlier.
Right, the ones that might explain the weird Hipparcos velocities.
Exactly. So these streams could be linked to those unexpected motions, further tangling up our picture of the warp. And missions like Gaia are actually still finding more of these lumpy bits like the Canis Major overdensity. Just shows how messy and active the outer galaxy really is.
Okay, so you've got the main warp, the weird way its stars seem to move, theories about the dark matter halo, and these extra streams and rings from past collisions possibly messing with things. Sounds like a real puzzle.
Yeah.
Then Gaia arrives, the game changer.
Absolutely. Gaia promised this huge leap in data, quality, and quantity. And the first data releases really started to shake things up.
How so? What did the early Gaia data tell us?
Well, in 2017, Pojo's group went back to some of those distant OB stars Hipparcos looked at, but now using early Gaia data from DR1.
And?
It was interesting. For stars relatively close to us, within about 1 kiloparsec or so, their proper motions did seem consistent with a kinematic warp, a warp defined by movement.
Okay, so it's there nearby.
But for the more distant stars, the data didn't really fit that simple warp picture anymore.
Huh. So the warp signal got fuzzy further out, even more complex.
Yeah, their thinking at the time was that a single, stable, long-lived warp probably couldn't explain all the systematic up and down motions they were seeing. Maybe the warp was more temporary, or maybe these other vertical motions were just hiding the real warp signal somehow.
And Gaia wasn't just looking at the big warp structure, but also those smaller ripples or waves hinted at before.
Correct. Schoenrich and his collaborators, also using early Gaia data plus older stuff, found this previously unknown wave-like pattern in the average vertical speeds of stars.
A wave. In the disk.
Yeah, particularly looking towards the galactic center and anti-center. It was a small wave amplitude about 1 kilometer per second, wavelength about 2.5 kiloparsecs.
Wow. What caused that?
They suggested this bending wave was likely connected to those monoceros and triangulum Andromeda structures, the rings and streams.
Ah, the galactic collisions again.
Possibly triggered by those past interactions, yeah. So it's not just a simple bend, it's more like a corrugated structure, almost. Ripples on top of the bend.
Okay, bent record now with ripples. So where did Gaia's second data release, DR2, take us? That data set was enormous, wasn't it?
DR2 in 2018 was just unprecedented. Millions of stars. Incredible precision. Poggio's team followed up again, looking much further out, maybe 7 kiloparsecs from the sun.
Wow.
They combined Gaia data with infrared brightness info, letting them look at hundreds of thousands of young, hot stars and millions of older giant stars.
Okay, this sounds definitive. Did DR2 finally give us a clear picture of the warp across the galaxy?
Yes, this was the breakthrough. For the first time, the large-scale motions of both young and old star populations showed a clear, consistent signature of the galactic warp.
Both young and old, that's important, right?
Hugely important. They saw this gradient in vertical velocities changing by about 5 to 6 kilometers per second, between roughly 8 and 14 kiloparsecs from the center.
Okay.
The fact it was in both young and old stars strongly suggested it's caused by gravity. It's a fundamental part of the galaxy's structure, not just some temporary glitch in the gas or young stars.
So Gaia finally nailed it down. The warp is real, it's large scale, and it's gravitational.
That was the big takeaway. It showed the warp wasn't just some local quirk, but a large-scale feature deeply embedded in the Milky Way's architecture. And it depends on age.
Ah, okay, so it's not exactly the same for young and old stars, another layer.
Exactly. Romero Gomez and collaborators dug into that with DR2 as well, looking at young OB stars versus older red giants, even further out. They confirmed the warp does depend on the stellar age.
How so?
Younger stars showed the warp starting further out from the center, and the bend itself wasn't as high vertically compared to older stars at the same distance.
Interesting.
They also confirmed it's not a simple, smooth bend. There's significant complexity, different wave-like patterns mixed in for both young and old stars. It's like the warp itself has structure.
So young stars, more gradual bend, starting further out. Old stars, more pronounced bend, starting closer in. Do we have numbers on how big the bend is?
Yes. At about 14 kiloparsecs out, the warp height for young OB stars was maybe 0.2 kiloparsecs. But for the older red giants at the same distance, it was much bigger, closer to 1 kiloparsec high.
Wow, that's a big difference, 5 times higher for the older stars.
Yeah. And other studies back this up. People looking at Cepheids with DR2 saw these big, warp-like vertical motions, like 10 to 20 kilometers per second amplitude.
Huge speeds.
And studies of OB stars, red clump stars using Gaia, plus other surveys like Lamost, they all pointed to this age difference, this complexity, and maybe even the inner disk starting to warp around 9 kiloparsecs out.
So Gaia DR2 really painted this incredibly detailed, complex picture, a fundamental, age-dependent, possibly rippling warp. What are the current models trying to make sense of all this richness? How do we explain it now?
Well, a lot of focus now is on the dynamics, how the warp moves. Cheng and colleagues, and Poggio's team too, have estimated the warp's precession rate.
The wobble speed again.
Right. How fast that bend is slowly rotating around the galactic center. Their estimates are around 10 to 14 kilometers per second per kiloparsec, somewhere in that range.
And how does that compare to the galaxy's rotation?
It's quite a bit slower. The galaxy's spinning much faster at our distance. They also tried to pin down where the disk really starts to flare out and warp, maybe around 8.9 kiloparsecs from the center.
Okay, so it's precessing slower than the main disk spins. What does this precession rate and the fact it seems consistent across different ages tell us about the cause?
That consistency across ages is really key. It tends to lean away from ideas about it being left over from the Milky Way's very early formation,
Why?
because different parts would likely precess at different rates and smear it out over billions of years.
Hmm.
The consistency suggests something more recent or ongoing.
Ah. So back to the galactic nudge idea.
Exactly. It strengthens the case for a relatively recent or even ongoing gravitational encounter with a satellite galaxy.
The usual suspects, Magellan Clouds, Sagittarius.
Those are still the prime candidates, yes. An interaction like that could impart a warp that affects stars of all ages relatively coherently, matching that consistent precession rate we seem to observe.
So a cosmic bump in the road from a smaller galaxy is the leading theory now. Have we cracked it? Is the mystery solved?
Well, not entirely. It's really important to stress that these models, these conclusions, they're still being actively debated and refined.
Oh, still contested.
Yeah, as Chang and others pointed out, even in recent work, there are still details that don't perfectly fit, aspects that are challenged. The big picture we have now, from cosmology and observations, is of a galactic disk that's just constantly being perturbed.
Right.
Gravitational torques, interactions, it leads to all sorts of things.
Yeah.
Wobbling, flaring, and warping like we see.
So studying our warp tells us about galaxies in general.
Absolutely. It gives us vital clues about how galaxies evolve, how they interact, and even helps us map out the distribution of that invisible dark matter. Our Milky Way is this unique laboratory because we're in it. We can get such detailed data.
A crucial case study then. But even with Gaia's amazing data, a complete universally accepted story for our warp, its exact motion, its ultimate origin, that's still just out of reach.
Precisely. It remains elusive. We're constantly refining things as more data comes in. Hopefully, future Gaia releases, maybe DR3, DR4, and other surveys will add more crucial pieces to this puzzle.
Help us finally nail down this fascinating feature of our cosmic home.
That's the hope.
Okay, let's quickly recap this deep dive then. We started realizing our galaxy isn't perfectly flat, but has this intriguing twist, this warp.
Right. Common in spiral galaxies.
We looked at early hints from young stars, Miyamoto finding that weird extra rotation.
But the why was missing,
Then Hipparcos confirmed the shape, but found those baffling opposite velocities.
leading to ideas of short-lived warps or disk wobbles.
We touched on the dark matter halo theory, its misalignment potentially causing a precessing warp, but dependent on its shape.
Which simulations suggest could be either prolate or oblate.
And we added the complication of the Monoceros ring and other streams, relics of past collisions that might be stirring things up.
Making the whole picture messier.
Then came Gaia. Early data hinted at complexity, finding waves.
And DR2 really delivered, showing a clear warp signature in both young and old stars.
Suggesting a gravitational cause, but one that affects stars differently depending on their age, and with its own complex structure.
Yeah, the height and starting point vary with age.
And current models, looking at the precession rate, lean towards a recent interaction with a satellite galaxy, like the Magellanic Clouds or Sagittarius.
But even that's not fully settled yet. It's still debated.
So as we've seen, it's a story still unfolding, huge progress, but the final chapter on the warp isn't written yet. It really shows how dynamic our galaxy is, doesn't
It
it?
absolutely does.
Wow.
Constantly changing, constantly reacting to its environment.
And with more Gaia data on the horizon, maybe we're getting closer to finally understanding our warped home. So as you think about this vast, complex, warped Milky Way, maybe consider this. What does this twist, this ongoing puzzle, tell us about the long, messy, turbulent lives of galaxies everywhere, and, our own tiny place inside one of these incredible dynamic structures?
A good thought to end on. And if you want a visual, you might look up that animation by Stefan Payne-Wardner at MPIA Heidelberg. It's based on Chen et al.'s work and really helps picture this warped precessing disk.
Definitely worth a look.